So what I have to showcase for you by the end of this video is an auto trainer and evaluator for LLM models and a chess that I've created. I can't run it for you in real time because if I run it in real time, my computer starts like smoking and I can't record anything at the same time. Like I just won't do anything else. So I'll talk you through this and we'll go through it and let's dissect this algorithm and dive into it. So first of all, how do I get here? The very first thing is this article that came out a couple weeks ago caught my eye, and I've been like thinking about it and pondering on it for a few weeks now. And it's called "Something Weird is Happening with LLMs in Chess." And then they do a cool experiment where they run every single LLM model against Stockfish. And then every single LM model gets obliterated by Stockfish, except for one. So Llama 3.2, just Llama 3.1, same thing, right? And we go through Quen, Command R, Gamma, GPT, and then so here's the exception, right? GPT 3.5 Turbo Instruct wins. GPT 3.5 Turbo loses. Terrible. Only GPT 3.5 Turbo Instruct out of all these models. And then GPT 4.0 Mini, terrible. 4.0, terrible. 0.1 Mini, terrible. And then so what we can see is literally the only good model within this is GPT 3.5 Turbo Instruct. Why that is, I don't know. No one knows, right? But that does give us a baseline to go off of, which tells us that models can in fact do this, right? If every single model is terrible except for GPT 3.5 Turbo Instruct, then there's something that we can do to flip that switch from terrible to excellent. And then so that's kind of where I start off this experimentation on my own, right? I want to see exactly what I can do here. And then so when we look at these graphs and we go through all these charts, you'll notice something, right? The models will make it to about 34, between 30 and less than 40 moves, and then they fall apart. And then so here we can see the same thing, right? And then so I experiment this out and I go through it with GPT, with these models on my own. And I start off with GPT 4.0, right? And then that's kind of the first place where I start off. And then my first hypothesis is that I want to have these models run and do these simulations in hyperbolic space as opposed to Euclidean space, which I've talked a lot about in my videos and going through. And my hypothesis for that is very simple, right? My hypothesis is that when you look at a chessboard and you break down a chessboard, bringing it and shaping it into 2D space from 3D space warps the image of the chessboard. And then so I think my hypothesis is that over time that warps the image that the model can essentially play with, and they don't understand, they lose track of the board state, even if you give them graph-based information around that. And then so that's my hypothesis. And then the very first experiment that I run is with a GPT 4.0. I ask it if it can essentially like simulate these things. Like, can you actually run a game in hyperbolic space? Let's try it out, right? And then so I try it out and I go through, I try to find different tools to actually do this online. I can't find any readily available tool. I don't know how the person that wrote this article did it. I'm not a big chess person, right? But so I go to like chess.com and all of that, and none of it works. So I essentially just set this up as an experiment where I'm like hand doing it, right? So I play as GPT. I move for GPT. I tell GPT where the computer moved, and then we go from there. And I just feed it like back and forth, right? And then here's the moves. And then I go through this, and then the first game that I play with this, we go through, and then so the very first game that I play with the model, I mess up around about turn 17 or so. I just flat out mess it up. But GPT is beating Stockfish up until this point, like kind of like devastatingly, right? And then so this second game goes to 48 moves total, and then up until ChatGPT blunders move 46. Up until move 46, it's absolutely face crushing. Like it's gutting Stockfish. Like there's no contest, right? Like ChatGPT has to like literally sacrifice away its queen in order to lose, and that's what happens. Right? And then it has like two queens, and then it like gives sacrifice, blunders them both away, right? But up until this point, like up until like turn 35, ChatGPT is just going and devastating like stockfish. And then I can tell that there's definite improvements over this hyperbolic space playing algorithm as opposed to in Euclidean space. So I do notice something there. But then kind of like what it seems like to me as I go through is like ChatGPT's like memory kind of fills up, right? And I do this experiment a few times, and it's exactly like really what this guy's research shows, right? Like right around, I can get it to go past this point, right? Where's the GPT-4o? Here we go. Like, I mean, this is pretty much what happens, right, with the model. Like right around like turn 35, like 35 here, you can tell like its memory just gets full, and then like this is exactly what happens, right? And then so I decide, okay, like let's test that out, and then so I create this program here, and then this is essentially I have it actually better representation of it in the GitHub repository, and then it's called Hyperbolic Gesture. And then it's very straightforward. What it is it utilizes hyperbolic embeddings and then the memory module, large language models, and then I tell it to play chess. The model that I'm utilizing in this instance and for this is the small LLM, the 360 million parameter model. Just highlighting that up front, right? Like I tried to at first load this with the 1.7 billion parameter small LLM, and my computer wouldn't even load the model. Like it just flat out said, no, like this code is not going to execute. You're going to like fry your computer. And then so I had to go down to the 360M. So up front, again, like this is, there's no way that I know of at least to not make this computationally expensive, because you're feeding the model, like what my goal is within this, right, is to have the model, to feed the model the information of the game, and then to have it pattern recognition and pattern recognize the game, and then build shapes and read the shapes off of that, very simplistically, right? I'm giving it a graphical representation of the game. This is all the graphical representation, right? 3D graph of the game. That's exactly what I want it to do, and so that's what it's doing here. It's kind of unreadable to a human, to an LM model. This is amazing data, right? This is all the data that it needs. This is the shape of the game. And then so that's kind of the data that I want it to feed, and then reconstruct that. But when I do that, like this is giving it the shape every single turn, and it's like exponential magnitude as far as computational, right? Computation. And then so this works, it executes, but what I'm running into now in this and then setting this up is definitely like memory issues, right? So that would be the next step. If people want to take this further, is there's got to be a way to reduce the memory consumption of this, and then to make this algorithm more memory, less memory intensive overall. And then how to do that, I don't know. Like I'm going to leave this project here. Chess isn't my like main project overall. I kind of just wanted to highlight this and to do this, to play around with hyperbolic space and everything that I've been doing within that. And I feel mission accomplished on that end. And I feel I have this GitHub repository here that I'll leave for anyone else that wants to build this project, possibly take it forward, this whole project. If you want to train LLM models on chess and etc., like kind of like how you would use, this is a reinforcement learning training algorithm for LLM models on chess overall. And so here you go. If you like this type of content, please like and subscribe. Thank you very much.